Hello students, hopefully you're all doing all right. And today's lecture is about renewable energy resources and technology. So what exactly are we going to learn today? So the learning outcomes is we are going to identify the types of renewable energy resources, the technologies, and also its applications. So as already mentioned previously, there are conventional energy resources that our country and also the world has been using. So these include resources such as coal, petroleum, natural gas, hydropower, and nuclear power. And we know that some of these are non-renewable energy. Okay, so for today, we are going to look more into the renewable types of energy. And that includes geothermal, biofuel, solar, hydroelectric, and also wind power. First, we will look at solar. So basically, solar energy is defined as energy from the sun. So if you think about it, around 1.74 times 10 to the power 17 watts per hour of solar power hits the earth. Okay, and basically, there are two types of solar energy. So it can be either thermal energy, where usually this includes processes such as concentrated solar power and also electric energy, in which photovoltaics are used. Okay, I'm sure that the latter ones is something more familiar to you guys, but the first one, thermal energy, is also very much related to solar energy. So as mentioned, there are two types, photovoltaics and thermal. So in photovoltaics, I'm sure that you guys are familiar with this kind of situation, okay, where we have PV photovoltaics installed around places where it can get direct sun exposure. Okay, and this is an example. If you have ever gone near School of Graduate Studies, UPM, so these are what has already been installed there, okay, in UPM. But apart from that, there's also the thermal energy related to solar, in which concentrated solar power is using parabolic reflectors or mirrors to concentrate sunlight and convert it into steam. Okay, so you know that this conversion, heat to steam and then driving a turbine, okay, this process generates electric power. Right? So that's actually two. Okay, it's not, when we talk about solar power, it doesn't necessarily mean only PV. It can also include other types of technologies as well. And we are going to look further into that. Okay, but we will start first with solar photovoltaics. So if you look at PV, the panels, they are made from silicon crystals. Okay, and they need to use high purity silicon crystals because it's one of the requirements to make the solar panels. However, silicon in pure form doesn't have any free electrons. So if you look at the figure here, stable silicon, okay, pure silicon, it acts as an insulator. Okay, its electron cannot move through here, okay, because it has four legs, okay, and this creates covalent bond. It's very strong. Okay. However, we can do doping. Okay, doping adds impurities to the silicon, and then it changes the bonding structure. Okay, so it depends on what type of doping is included. So one type of it is N-type semiconductor. So N-type here, N means negative, You can already think about that. Negative means it has a surplus of electrons. Okay. Why? Because when it's doped with phosphorus, the silicon will have 5 electrons instead of 4. Okay, and the 4 electrons is bonded covalently, but there's 1 free electrons there. Okay, and that can be discharged from the arm and move freely. At the same time, if you change the component, the doping component, to something like boron, okay, so when boron is doped into the silicon, you will generate atoms that lack 1 electron. Okay, so in contrast to the n-type, p-type, it has holes, okay, where there's there's a lack of electron, okay, and that is called holes. How does all of this work together in PV? We look at that here, right? So in the normal PV flat panels, okay, usually they will manufacture the p-n junction. Okay, p-n junction is formed by placing p-type and n-type semiconductors next to each other. So something like this. So remember just now, p-type, it has less electron, okay? And naturally, you will attract the surplus electron from the n-type. Okay? Because remember, it always, atoms will always work towards stability. Okay? They need stability. So if they have less electrons, they will attract the free flow electrons from elsewhere. So that's where this comes handy. Okay? So basically, the electrons in the n-type layer, okay, if you look here, the n-type semiconductor, it contains more free electrons, and this will diffuse into the p-type layer, okay, while the holes will diffuse into the n-type from the p-type. Okay. However, if you look here, there's a depletion region. So usually this is the solution, or it's a barrier where electrons cannot pass through. So what happens is that it needs to go through the electric field, okay, and this generates a flow of electrons. So imagine you have a wiring here. We are talking about a basic construction of PV cell. Okay, so you have this as the PV flat panel, and then this is where your voltage is generated, or you can monitor the voltage being generated. Okay, so you have the movement of electrons from this side to this side. Because it's unable to go here, it will be forced to go through this route. Okay, so this kind of flow generates the electricity. Okay, and this is one. So imagine we have an array of solar panels, and all of these, the mechanism is similar, and it converts basically solar energy into direct current electricity. Okay, so always remember, solar PV, it generates DC, okay, direct current. So if you think about that, and you look at your house appliances, okay, most of them uses AC, alternative current, right? So that means you cannot directly use the electricity from solar photovoltaic. So there will be an inverter, okay? So after this, the electricity will be connected to an inverter where the DC will be converted into AC, and then it can be supplied to households, right? So that is about PV. Now we look at thermal solar. Okay, so if you still remember just now, we talked about concentrating thermal power, or CSP. Okay. So in CSP, there's actually 3 types of systems. There's throw systems, power tower systems, and dish engine systems. Okay. We'll go briefly across all 3, okay, just to give you an idea of what is happening in each type of systems, right? So in throw systems, the system actually uses large parabolic reflectors. Imagine you have focusing mirrors, okay, that have oil-filled pipes running along the center. So basically, this is the throw, okay, and you have the pipes here. So these pipes contain the fluids. So usually it has oil, okay. And then what happens is that the mirror will focus the sunlight, okay, into this tube. Okay? And you can imagine as the solar power is concentrated, it generates heat and the oil will start to boil, okay? Because it can achieve a temperature of around 400 degrees Celsius. Okay? And then, of course, the oil will be used to boil water and then, generates electricity using the turbine and generator. Okay. Next, we have power tower system. Okay, so this is an example. It looks very nice, isn't it? So what happens is that it has many flat heliostats. Okay, these are heliostats, or you can see this here. So it actually tracks the movement of the sun. Okay, and it focuses the rays onto the receiver. Okay. So the tower, the top of this is the receiver, right? So using the same concept as before, you have concentrated sunlight, okay, and this concentrated sunlight is very, very hot. So you can use that to heat the fluid. So usually in this type of systems, they use molten salt, okay, and the fluid will be heated to as hot as 565 degrees Celsius, okay, and then the hot fluid was used to generate steam for electricity generation. So if we look at that, all the systems, okay, it's basically you're using solar power, okay, and turn the heat into usable energy in the form of electricity. Okay. So that is something, that is the mechanism that is almost consistent with a lot of renewable energy resources that we have. Okay. So have a think about that, right? The third one is the dish engine system, right? So in dish engine system, it uses parabolic dish of mirrors, okay? So it's a little bit different than the throw system because of 2 things. First is these are usually this, and it's usually quite modular. Okay, it can be used. It doesn't have the capacity as high as the other 2 before. Okay, but it has the advantage of modularity, so it can actually be installed, even in places where there's less space, for example, okay, or the requirement of energy is not that large. So if you have like for one whole house, okay, you may need a few of this system, okay, but it would be enough to cover the energy expenses. Right. So what's the second difference is that instead of using turbines to heat up, instead of using the energy to heat up water into steam that turns a turbine, this kind of system uses engines. Okay, so this is an example of Stirling engine. Okay, and this system is integrated with a high efficiency external combustion engine. So you can imagine the engine, it has thin tubes filled with either hydrogen or helium. Okay. And then as concentrated sunlight falls on the receiver, it hits the gas in the tube to a very high temperature. And then that high temperature, okay, the fluid that is very, very hot is used to move the piston in this type of ways. Okay, so you can look here, it's hot, and this will drive the engine. Okay. So usually it uses Stirling engines for this kind of system. Okay. Now this will create mechanical power which drives a generator and then produces the electric. Okay. So I hope it's clear. It's quite different. Okay. So instead of using turbines, we're using engines. Okay. But this kind of system, remember, it produces smaller amounts of electricity. Okay. But it has the benefit of being modular. All right. Next, we look at very briefly at the advantages and disadvantages. Okay. So, of course, the advantage of using solar energy is that, you know, across the world, we do have access to the sun. Okay. And especially in the developing regions, we have access to a renewable type of energy, okay, that are stable. Okay. It may be quite costly in the beginning, but the operating cost is acceptable for the long term. And then the return of investment is quite good, right? It is very environmentally friendly because, of course, it doesn't use any fuel. Okay? So it's not affected by the supply and demand of fuel. And of course, it's very clean, it's renewable, it's sustainable. And it has very low maintenance to maintain the systems. Okay. However, it does have its own disadvantages. It's very high capital. Okay, so a very high investment is needed at the beginning. Okay. And then it requires a large area for installation to achieve a good level of efficiency. Okay, this is one of the arguments against solar, because you will need a lot of land, right? And that land could actually be used for other things. So, for example, agriculture. So we have this discussion about food versus energy. Okay, which one is more important? Because we know that food security is becoming a very big issue. Okay, this is why one of the reasons why solar energy, a lot of people are using this type of arguments against solar. Of course, there's also other ways around this. You could always build your solar field on top of unusable lands. Okay? For example, you can even do it on top of water bodies. Okay? So, some alternatives. Another thing is the presence of clouds and pollution in the air may also affect energy production. Okay, and it is discontinuous because it depends on the availability of sunlight. Okay. And that follows when at night there will be no production of power. Okay. Efficiency, despite advances, there is currently only about 15% conversion rate of solar energy into electricity. Okay. And lastly, it requires a decentralized infrastructure. because you need to have usually in cities, okay, you can build your PV, but you won't have enough land, okay, especially in cities. Okay, so it needs to be further away from cities where the land availability is better. Okay, that's why we see that in cities a lot of the solar power usually caters to one building, so it's basically individual based rather than something that produces electricity for the grid. Okay. So I hope that's clear, because we are going to move into the next type of renewable energy, which is hydropower, right? So I'm sure that you guys are familiar with hydropower. So what exactly it is? So hydropower is generation of electricity using the flow of water as the energy source. Okay, and it basically depends on the water cycle. Okay, we have water that evaporates from the water bodies, condensation, undergoes condensation, and then precipitation. Okay, and that creates the flow of water. Because usually this is our source of water, right? So imagine when it's raining on top of the mountain. Okay, remember back when we talk about potential energy. Okay, so things that are elevated at higher height, they will have more potential energy. And this is the potential energy that will be used to be converted into electricity, okay, in terms of hydropower. So in hydropower, how exactly electricity are being produced? Okay. So of course, it uses, again, turbines. Okay. But before we go further into that, I'm just going to talk to you about the different categories of hydropower. Okay. So as we all know, water must fall from a higher elevation to a lower one to release stored energy. Okay. And the difference between these elevations, okay, the water levels in the forebay and the tailbay is called head. Okay. So if you have forebay here and afterbay there, so this height is called the head. Sorry about my handwriting. Okay, so that is the head. That is the potential height, okay, that you can actually calculate. Right? And of course, when we're talking about hydropower, there will be dams built. Yeah, and these dams can be characterized or categorized into three. Okay, we have high head, medium head, and low head, and that is categorized based on the height difference. Okay, so if you have the height which is more than 100 meters, it's called high head, okay, like this. Whereas if it's 10 to 100 meters, it's medium head. And lastly, we also have hydro power plants where it only uses low head, so it's less than 10 meters. And if you are going to calculate the power, power is proportional to the product of head times flow. Okay, so the flow of water times the head. Okay, the height. Now, there's actually different types of turbines if we're talking about hydropower. Okay, so it's categorized into two. Okay, there's reaction turbines and there's impulse turbines. So for reaction turbines, it actually derives power from pressure drop across turbines. Okay? And usually this type of turbines are fully immersed in water And the angular and the linear motion is converted to shaft power, right? So an example of this are propeller, Francis, and Kaplan turbines. So like this. So B is Kaplan and C is Francis, right? Whereas in contrast, we have impulse turbines, which convert kinetic energy, water jets, heating the buckets. Okay, so usually the turbines have buckets like this. So FYI, this is a Pelton turbine. You can notice the buckets there. So what happens is that the water flow will fall onto the bucket and turn it. Okay. And in this type of turbines, there's no pressure drop. Okay. And the movement, this will generate the electricity, right? So there are obviously some controversy regarding hydropower, okay? Because one of the most basic things is that it requires the development of vast amounts of infrastructure. Okay, there is a need to build dams. Okay, there needs to be reservoir of water. And then with that, there's also you have to construct the power plants and power lines. Okay. So these are very, very expensive. That's one thing. Economically, it's very expensive. Okay. But the second most important thing, I should rephrase that. Okay. So the second thing that is also important is the environmental problems that relates to this. Because the dams, when you build the dams, it alters the environment in the areas where they are located. It can change the nature of rivers, can create lakes. Okay? It's going to change the ecosystem, right? And how far are we willing to go, right? Which is why, although hydropower is very, very, it generates a lot of power. So if you look at in China, the Three Gorges Dam in Hubei province, it produces about 22,500 megawatt of electricity. Okay. And this is comparable to 30 conventional power plants. Can you imagine that? So 30 power plants, okay, the same capacity is produced just by one dam. Okay, so you can imagine how much electricity, how many households you can cover, okay, just by having this. But of course, there's the disadvantages. Right? So pros and cons. The advantage, of course, it's emissions free. There's no carbon dioxide, there's no NOx, SOx, no hydrocarbons, no particulates. So if you compare that to the conventional power plants using coal or other petroleum resources, it's definitely very clean, right? And it is a renewable resource with high conversion efficiency to electricity because it can actually generate more than 80% electricity conversion. And it's scalable. It can be from 10 kilowatt to 20,000 megawatt, like what we looked at before with Three Gorges Dam. Okay. And then it has a low operating and maintenance costs, and it lasts a long time. Okay. But the disadvantages, of course, it frequently involves large amounts of water impounded. Okay. And this leads to loss of habitat due to land inundation. And secondly, the output is also variable. It's very dependent on rainfall and snowfall. So snowfall if it's in, cold climate, right? So the impacts of hydropower plants, it also has impacts on the river flow and aquatic ecology. This includes fish migration and oxygen depletion. And of course, it also has many other related impacts, such as social and health impacts, right? It is costly in the beginning, so the capital is quite high, because imagine you have to construct all those dams, reservoir, everything. Okay? And it takes a long time because it's a very large project, and there's a lot of problems usually, okay? And it has to be solved before you will be able to start the hydropower plant. Right? So if you think about water, straight away we think about hydropower plant, right? But actually there's other types of energy, okay, which relates to water that can also be manipulated. Okay. One of those is tidal energy. Okay. Tides are vertical rise and fall of the sea level as a result of gravitational attraction between the Earth, the Moon, and the Sun to a lesser extent. So how does a tidal plant operate? If we look here, so imagine this is the ocean, and this is the land. This is where you are. So in a tidal plant, okay, during the period of high tide, okay, the gate will be open, okay, and the water will be able to enter the reservoir. Okay. Now, at this, when it's filled up, okay, the gate will be closed, and then you look at the tide as the tide at low tides. Okay, this gate will be open, and you have the potential energy here, where the water will flow out, and there will be a turbine here. Okay, and the flow of water from here to here, yeah, will turn the turbine and generate electricity, of course. Okay, so imagine the water is going out, okay, until it reaches the lowest point, after which the gate will be closed, right? And then when the tide is increasing again, at the highest point, the gate will be open again, okay? And now we have the potential here. So water will actually move the opposite way, okay? And the turbine is designed in such a way that it can be turned in both directions. So during this situation, it turns one way, and in the second situation, it turns the other way, okay? And both movements will generate the same amount of electricity, right? And then, of course, as the water goes up, where you get this kind of situation, the gate will be closed, and then this cycle starts all over again. Okay. So apart from tides, there's also waves. Okay, that's wave energy. So waves are generated by the wind as it blows across the sea surface, and the energy is transferred from the wind to the waves. Okay? And if you look at waves, yeah, waves travel vast distances, okay, at great speed. So it actually depends on the wind. The longer and stronger the wind blows, okay, the higher, longer, faster, and more powerful the waves are, right? So wave systems can be classified as shoreline devices, nearshore devices, and offshore devices. So you can look at the figure down here, okay, where you have shoreline devices, which is fixed or embedded in the shoreline, okay. or you can have near-shore devices, right? So there can be two types of situation where it's either at have a bottom standing or it's floating, okay? And the wave power is extracted directly from the breaker zone, and the waters immediately beyond the breaker zone, which is at 20 meters water depth. Right? And lastly, with offshore devices, of course, that is the farthest one up, farthest out to sea. Okay. So there are four basic wave energy capture type methods, right? Point absorbers, wave attenuators, oscillating water columns, and overtopping spillover devices, right? So don't worry too much about this as long as you understand how the energy from the waves are captured, then you'll be fine. Okay. So this one is actually it's an emerging type of technology. So it's called ocean thermal energy conversion, or OTEC. Okay, and OTEC, I decided to put this under the water resources, although it could also technically it can be categorized within the thermal type of energy. Okay, so what happens here is this type of systems, it uses the ocean thermal gradient between the deep water sea, okay, where the temperature is cooler, okay, and the warmer shallow or surface sea waters. Okay, and you have basically you have a temperature difference between the two, and this temperature difference will run a heat engine, okay, and produce useful work, usually in the form of electricity. Okay. So it can be either a closed system or an open system. Okay. In a closed system, it uses fluid with low boiling point, such as ammonia, which is vaporized using the warm seawater through a heat exchanger. Okay. Whereas in open system, so remember open, you can already relate to any types of situation. So open means you will use the warm surface water directly, where it is vaporized at low pressure. Okay, so in closed system, it uses a different type of fluid. In open system, it uses the seawater directly, right? So it's quite efficient, okay, up to 3 to 4% of energy conversion. Okay, but basically you need a larger temperature difference to ensure a higher energy conversion efficiency. Okay, so what happens is that as you go down, okay, in the sea depth, okay, as you go down, the temperature will be reduced, okay, and there will come, there will be a depth where the temperature difference is no longer that much. So if you look at the graph here, okay, so around 2000 around 2000 meter depth of the sea, the temperature will be around 4 degrees Celsius. Okay, so please pardon the drawing. Okay, so and then if you go even lower, there's not much difference anymore, right? So you can imagine if you have a depth of a certain depth, then you can definitely use the system to generate electricity. Okay? Because it only uses the temperature difference of the water. So basically, okay, this is the type of closed system. okay, where you have a type of gas, a fluid. So this one is driven by ammonia. Okay, so if you ask me why ammonia, so ammonia, it has a low boiling point. So if I'm not mistaken, something around -30 or -34 degrees Celsius, it will start to boil. Okay, so it exists. So in this or this type of fluid, you only need less heat, okay, to boil it up if you comparing that to water. Okay, so you have the warm seawater. That warm seawater will will heat up or vaporize your fluid. Okay, and the fluid will move into the turbine, turns the turbine, okay, produce the power that you need, all right, and goes into the condenser where the water, the cold water, will drive the condenser. Okay, and the heat exchange that is done here as a system basically is the one that drives the electricity generation, right? So that's it for water. So we move on to the third type of energy, which is the wind energy. Okay. Wind is actually a form of solar energy and is caused by the uneven heating of the Earth's surface and the rotation of the Earth, right? So the greater the pressure difference between these areas, the harder the wind blows. So wind has actually been a source of energy for over 3,000 years. So, people in the medieval ages, they have used that. Okay? And it's an important part of many communities around 1200 BC, where they use it to grind grains and to pump water. Right? That's where, it's a very iconic images. Okay? So in Netherlands, for example, okay, the first one is in Netherlands, the second one is in Spain, the third one is in Sweden. Okay, so basically, these has been used for a long time already. And basically, it converts kinetic energy in the wind to mechanical power, right? So this is what has been done with the medieval people. But now we, as the people of the earth, we are now using electricity as our energy. So it requires the generator. Okay, we have that mechanical power, which is converted into electricity using a generator. Okay. So in wind energy, okay, the windmill design is very, very important. So the efficiency will depend on how the windmill is designed. And some of the design considerations are the size and design of the turbine and generator. Okay, so if we look at the size, okay, we have large and small turbine sizes. Okay. And of course, with large turbines, you will be able to deliver electricity at lower cost. And it's very well suited for offshore wind plants. Okay. And in areas where it is difficult to find sites, one large turbine on a tall tower uses the wind extremely efficiently. Okay. That's if we are using large turbines. However, there's also small turbines, okay, where local electrical grids may not be able to handle the large electrical output from a large turbine. Okay, so this type of situation may happen, okay, because sometimes this will become clearer once we learn about the electrical grid. Okay, I think this will be covered in our next lecture. But basically, just to give you an idea, the electricity grid has its own demand. Okay? And the demand will be supplied based on the available power plants. Okay, so there's a limit there, so it cannot receive more than it can handle. Okay, which is why it is also useful to have small turbines. Okay, because sometimes when there's too much power, it's not a good thing as well. Okay, especially if it cannot be stored. All right. High cost for foundations for large turbines may not be economical in some areas, which is why small turbines would be a better choice. Okay? And of course, another thing that relates to small turbines is the landscape consideration. Okay, so imagine that is an area where you cannot build large turbines. Okay, smaller is the way to go. Okay, and apart from the size, okay, you also need to look at the number of blades. Okay, because the most common design is actually the three-bladed turbine. Okay, and this has its own reason because it's very stable if you have the three-bladed design. Okay. But interestingly, if you have even numbers, okay, there will be some stability problems. Okay, and this relates to the pressure difference, of the fluids, okay, the air, how it moves, okay, and how the blade will actually, how best, how more efficient the blade can be turned, okay, with regards to the wind that is available. Right. So this is an example of a wind turbine. Okay, you have the blades which catch the wind and spin. Okay, and as it spins, okay, look here, you will have the generator, because that mechanical energy, okay, can be converted into electricity. Right? And then once the electricity is produced, okay, you have the cable lines, and that cable will carry the electricity to the transmission line. Okay. So we talk about the size of the turbines just now, but another design consideration is also about the wind turbine generators. Okay, there could be small generators or there could be large generators. Okay, so in small generators, it's actually require less force, okay, to turn than larger ones. But of course, with small generators, you can expect a lower power output, okay, and it's actually less efficient. So if you have a situation where a large wind turbine is fitted with a small generator, okay, it will produce electricity during many hours of the year because you only need low speed of wind, okay, and that will be able to turn the turbine. However, it can only capture a small part of the energy content of the wind at high wind speeds. Okay, so contrast that with a large generator. Okay, it's very efficient at high wind speeds. Okay, but in a situation where the wind speed is low, it won't be able to be turned. Okay, and you won't be able to get any electricity. Okay. And of course, if you look at the generator, large generators will either have larger coils or it has a stronger internal magnet, which is why more force is needed to start its movement. Okay, so that's why if you compare small and large, right, there are pros and cons for each of them. Okay? And which is why the design consideration is very, very important. So you have to look at the wind profile of that area, think about what are the energy capacity that you need for that area, all right, and how much your design will be able to supply the electricity to that area. Okay, so the design aspects are very important. So to sum up the advantages and disadvantages of wind energy, with of course the environmental benefits cannot be argued against. It's very clean, has no emission. Right? You don't even need fuel, and wind actually blows day and night. Okay? So if you contrast that with solar power, for example, with solar power using PV, okay, we won't be able to get any electricity if the sun is not there. Okay? When it's nighttime, you won't be able to get electricity. But this is different with wind because it's available day and night. So you will be able to get continuous electricity. Okay. However, it has disadvantages. First is it's very low power density. So you will need a very large number of windmills to produce a modest amount of power. Of course, wind is unpredictable. There could be situation where no wind blows at all right? And you won't be able to get electricity in that kind of situation. The cost, it's very high capital cost, right? And it does have its own environmental costs. Basically, with regards to material use, right? The maintenance costs, and then the noise, because people, if you read reports of people, okay, where they complain about the noise from the windmills, okay, it happens, okay? And then birds, okay, there are situations where birds run headlong into the windmills and dies, right? And lastly, the appearance. Okay, some people just doesn't like the unnatural appearance of windmills. Okay, in in nature. Okay. And if you think about it, another thing is that you cannot meet large scale, okay, and transportation energy needs because you are producing low power density and the energy is in the form of electricity. All right. So we move on to the fourth type of energy, which is geothermal energy. Okay. The geothermal energy is heat derived within the subsurface of the Earth. So as we go down further to the core of the Earth, the temperature skyrockets. Okay. So 2 to 4 miles below the Earth's surface, rock temperature is well above boiling point. Okay. And there will be a geothermal reservoir, okay, where hot water and steam is trapped in permeable and porous rocks to form a geothermal reservoir. So this reservoir can be discovered by testing the soil, or you can analyze the underground temperature. It is possible. And another indication is the areas where you can see geysers, boiling mud pots, volcanoes, and hot springs are found. So if you see this type of vents, okay, so for example, geysers or boiling mud pots, you can be sure that there are geothermal reservoir underneath that. Okay. So basically, in geothermal energy, okay, you want to make use of the heat, right? And this heat can be brought to the Earth's surface either directly. Okay, so this is usually from hot springs or the geysers, or you can also use geothermal heat pumps. Okay, and although these are quite general, okay, you can actually classify the uses into two. First is direct use, second is indirect. So for the direct use, okay, it is used directly, okay, the heat is used directly in hot springs and spas. So this is for recreational or health benefits, okay? Or it can be used for heating purposes. So the water, the hot water, is used in fish farms, buildings, drying crops, and greenhouses. Or it can be used to provide heat to industrial processes. Okay? And indirectly, the heat is used to drive the turbine, okay, which then generates electricity through a generator, right? So what happens in the geothermal power plants? So there's actually three types of power plants. We have dry steam power plant, flash steam power plant, and binary cycle power plant, right? So in dry steam power plant, you actually use so before we go into what exactly is these three types of power plants, okay, so I will just give you a brief description about what happens in a typical geothermal power plant. Okay. So you have cold water from the surface, which is pumped under pressure down an injection well, okay, into the reservoir. Okay. So because of the hot temperature in the geothermal reservoir, we heat up the water and the hot water returns to the surface under pressure, right? So in dry steam power plant, okay, what drives the turbine is pure steam. Okay, so you have the water, which is fully boiled, and all of them are steam, okay, and that will drive the turbine. Okay. In flash steam, okay, the water that comes down is still water, okay, when it comes up, and then the pressure will be tweaked, okay. So in this type of situation, the chemical term for that is actually flash, okay. So it will be flash, and it means that the flow here, okay, that goes into the turbine, okay, is a mixture of steam and hot water, right? Whereas in binary cycle, which is this one, this picture, it actually uses the water, the cool water, heated up, and then when it's very, very hot, okay, it goes into a heat exchanger, okay, which then heats another fluid, another type of fluids, right? And that fluid is the one that is boiled and then turn the turbine. Okay, there's three types there. All right. So with geothermal energy, okay, the advantage is that it is available all year round, okay, because the geothermal reservoir has the heat, okay, and it can provide the heat continuously. It does not involve any fuel combustion. It is independent of weather. And it is very cleanly sourced. Okay, very little emission or overall environmental impact. However, it is not widespread. Okay, if you look at the location of geothermal reservoir. Okay, you have to screen for that. It won't be available everywhere. Okay, and as such, it has a very high installation cost. Okay, and it is possible that you can run out of steam. Okay? And because the reservoir is underground, okay, and trapped within porous rocks, it is possible that this kind of reservoir also contains other gases, okay, harmful gases, for example, and that will relate to the safety. Okay. Next is the transportation, and this relates to how you're going to transport the electricity generated. Okay, and lastly, it is also possible to use earthquakes. Okay, because basically in geothermal energy, it relates very much to the tectonic movements, okay, within the earth. Okay, if we are changing something, we can expect that there will be a reaction. Okay. Right. So now we move on to the next type of resource, okay, which is biomass. Okay. Biomass is a renewable resource. That's definitely true. Okay. And what it is an organic material that comes from plants and animals. Okay. So basically, if you look at biomass, it contains stored energy from the sun. Okay. Because if you look at plants are actually the primary producers. Okay. It generates its own food. Okay. It produces oxygen, it fixes CO2, okay. It performs photosynthesis. And then you have animals as you go up the food chain. Okay, the animals will use the plants, and make use of the chemical energy to provide as food and also as energy source. Okay? So if you think about it, fossil fuels also originated from biomass, although this is a process that takes millions and millions of years. Right? So basically, if you just look at biomass, okay, as very, very general, brief look at biomass, there are many uses of biomass as an energy resource. Okay, so going briefly here, you can have wood and wood processing waste, which is burned for a source of heat. Okay, or you can use that to generate electricity, of course. You have agricultural crops, or you have agricultural waste, right? And that also can be burned or converted into biofuels. You also have food waste, okay, what you throw out from your own house, yeah, from the residential areas. This type of waste can be burned to generate electricity, or it can be converted to biogas in landfills, okay, or anaerobic digestion. Okay. Lastly, animal manure and human sewage also can be converted to biogas. Okay. And biogas can eventually be used as a fuel. Okay. Which is why biomass is a very, very interesting renewable resource. Because if you think back about the 4 types of energy resource that we've looked at before, okay, all of them produce electricity. Okay, all of them. Like biomass, you can also produce fuel. Okay, because remember, energy does not only mean electricity. Okay, there's different types of energy required in daily life. Okay, you need fuel for transportation. Okay. Electricity, of course, that is required. And also, there are some places which require heat. Okay. So if you look at the sources of biomass energy, okay, this is quite a simplification. Okay, there are so much more, but if you can have trees and plants, okay, and this can be agricultural waste or energy crops. So crops that are purposely planted, okay, in order to produce energy. Okay. So you have animal waste, you can have crops. Okay, just now I was talking about energy crops. Okay, you can have wood products, food waste, a lot of many other types of biomass as well. So if you look at the variability of the biomass source, okay, it's also interesting to note that there are many ways to convert this biomass into energy, okay, in whatever form that is required. Okay, so basically, in general, it can be categorized into 5 types of conversion. Can be thermal, can be biochemical, it can be chemical, can be electrochemical, or it can be mechanical. Okay, so please bear with me. We will go briefly on each of these. All right. So in thermal conversion, it uses heat to upgrade the biomass into more practical fuels. Okay. So it has 4 alternatives depending on the chemical reactions based on oxygen availability and the temperature. Okay. So the 4 includes combustion, have torrefaction, have pyrolysis, and gasification. Okay. And actually, there is another emerging thermal conversion called hydrothermal liquefaction. And then for biochemical route, so basically, in biomass, although you can have many sources, in general, especially plant biomass, it contains 3 major components, which is cellulose, hemicellulose, and lignin. Okay, and these components can be processed biochemically to produce useful products. In biochemical processes, there are 3 types of process. It can be anaerobic digestion. Secondly is fermentation. And lastly is composting. Okay, so you can use either of these 3 to convert the biomass into the useful type of fuel, for example. Okay. The third type of conversion is chemical. So basically, it uses chemical processes to convert biomass to other forms. Okay, and in this type of process, so one of the most famous or the most general one used is FT synthesis or Fischer-Tropsch synthesis. Okay? And in this process, biomass is converted into multiple commodity chemicals. Okay? So FT synthesis is actually very common use currently in petrochemical plants. Okay? So the same techniques can be used to convert biomass into different types of petrochemicals, okay, that is currently being produced now. So other than chemical, electrochemical conversion is also possible, okay, where you can directly convert biomass into electricity via electrochemical oxidation. So this is generally it generally relates to fuel cells. Okay, so you can have something like a direct carbon fuel cell or microbial fuel cells. Okay. And lastly, number 5 is mechanical conversion. Okay, and this involves mechanical processes such as crushing, compressing, and pelletizing, where you can produce solid fuel from the biomass. Okay. And examples of that is fuel briquettes. Right? So this is actually an overview of the concepts, the process related, and what are the type of energy that can be produced from that. So the first type of conversion is thermal. Okay. Thermal biomass conversion, it's generally related to the availability of oxygen and also how high or how low the temperature is. So you have complete combustion, okay, which requires the most heat, where you will be able to get heat and power and water and CO2. So if the temperature is 700 and above, it goes through the route of gasification, where you will produce syngas. And in syngas, there's different types of products that will be produced. So you can have H2O, okay, CO, carbon monoxide, hydrogen, carbon dioxide, and you can have various hydrocarbons. Okay. At the same time, tar and char will also be produced. Third one is pyrolysis. Pyrolysis is usually a process where the temperature is around 400 to 650 degrees Celsius. Okay. And this type of process will produce bio-oil. So along with that, it also produces CO, carbon monoxide, carbon dioxide, water, organic vapors, and char. Okay. So if you go lower, 200 to 350 degrees Celsius, it is a process called torrefaction, where the biomass is converted into non-condensable gases, water, organic vapors, and char. Okay. And lastly, we have the 5th option, which is the HDL. Okay. And in HDL, actually, it is an emerging technology, okay, where you have your biomass and you can actually produce different types of hydrocarbons. Okay, and this is very interesting if you look at producing fuels for transportation. Okay. Because in the gasoline that you use in your car, okay, contains various chain lengths, carbon chain lengths of hydrocarbons, right? So HDL will be able to generate something similar depending on the design of your HDL system. And another important thing as well is that with the other types of processes, water is an issue. But with HDL, you can actually use the wet biomass. Okay, that's no problem. So you can, it basically removes the requirement to remove water from the biomass, which is a very big issue with the other processes. Okay. So aside from thermal, we have biochemical biomass conversion. Okay. And of course, if you are using AD, anaerobic digestion, okay, there's many types of biomass that you can use as the substrate. Okay. You can use livestock waste, you can use crops, you can use wastewater, food waste, you can use agricultural waste. Okay. And the process will generate biogas and digest it. Okay, and the biogas actually can be used directly to produce heat. You can you can burn it to produce heat, or you can produce electricity from it in power plants. Okay, or otherwise you can upgrade the biomass, okay, by purifying the biomethane, and that biomethane can be used as fuel. Okay, or you can include that into the gas grid, but also, of course, this is more relevant to the coal countries, okay, where they use gas to produce the home heating systems. So not only the biogas is usable, the digestate is also very, very useful. You can use that as a fertilizer. You can use it as a soil amendment, or lastly, you can use it as livestock bedding. So that is for anaerobic digestion. You also can go through the route of fermentation. Okay? And in fermentation, if you look at the simple process of fermentation, it actually involves some type of sugar. Okay, and then you have your microbe. Okay, so in this figure, it uses yeast, but it can also be other types of microbes as well, such as bacteria. You can use algae, right? So in fermentation, okay, it is conducted in the absence of oxygen, where you will be able to produce carbon dioxide and also alcohol. Okay. So this is a simplification, because other than alcohol, you can also produce different types of fuels. Okay, so you look here, you can produce bioethanol, you can use biobutanol, biohydrogen, ABE, or otherwise known as acetone butanol ethanol. Okay. And you can also produce biodiesel. Okay. If we're talking about biomass, so this is from sugar. Okay, it's very direct conversion. But if you have biomass, okay, so remember just now I mentioned in biomass you have different components. So you have cellulose, hemicellulose, and lignin. So in fermentation, the lignin bit is non-usable. Okay, so you have to remove the lignin first. Okay? And after the lignification, it undergoes hydrolysis, okay, where the cellulose and hemicellulose will be broken into much simpler sugars, okay, and then that will be fermented by the microbe of your choice, okay, into the type of biofuel of your choice. So it totally depends on your own design. What types of microbes you use will give different types of biofuel. Okay. And of course, if we're talking about biofuels, there are actually 4 generations now. Okay, in the first generation biofuels, it uses edible biomass. Okay? If you look at the case with Brazil, okay, they use sugarcane to produce ethanol, okay? And it's an industry that has been there until now. Okay? They are at the forefront of the ethanol, using ethanol as a biofuel. But then again, we have the issue with food security. So the food versus energy argument has caused the emergence of second generation. Okay? So second generation biofuel uses non-edible biomass. So you can have the agricultural residues, or you can actually plant specific energy crops. Okay? So example of that is switchgrass. Okay, there are other types of plants, energy crops as well, that are being planted in order to produce the targeted biofuels. Okay? And then third generation biofuel starts to emerge. Okay, with third generation, it uses algae biomass. So what's different about algae is that it's basically it performs photosynthesis. So instead of having only biomass, so the agricultural residues, for example, you can actually use the algae itself to produce the fuel. Okay, and if you look at the energy accounting of that, what comes in is only the CO2. Okay, and looking at climate change now, okay, where you have an abundance of CO2 in the atmosphere, this looks like a very logical answer, okay, to prevent climate change, or actually to reduce it. Okay, you have to slow it down, right? So algae biomass is an emerging type biomass used produced biofuels, okay, and that relates to the use of macroalgae and microalgae. And during the advances with third generation biofuel, fourth generation comes out. Okay, and in fourth generation, actually, it relates to genetic modification. Okay, so you can actually engineer the algae, okay, in order to increase the energy efficiency, the solar fixation, and also the production of the fuel that you want. Which it can be hydrogen, can be bioethanol, can be biobutanol, anything. Okay. So that's why it's very, very interesting. Okay. So looking at that, right, algae-based third and fourth generation biofuels, it's algae-based. So algae are autotrophs. They perform photosynthesis to fix CO2 from the atmosphere into its own biomass. It produces many types of fuels and products, either naturally, where we call it the third generation biofuel, or through genetic manipulation, which is the fourth generation biofuels. So if you look at algae to energy, and you look at algae as a whole, okay, the most interesting thing about algae is that it has many different components. It has carbohydrate, it has protein, fatty acids, terpenoids, okay? And each of these can be used to produce different types of fuels. So depending on what exactly the fuel that you want, okay, you can tailor-make that according to what type of algae that you are using. Okay, so for example, the carbohydrate portion can be fermented to bioethanol, biohydrogen, and biogas. Whereas protein, you can use that in AD to generate biogas. The fatty acids and lipids portion can be transformed into biodiesel. And the terpenoids can undergo chemical processes to produce diesel substitute. Okay. So this can be in the form of bisabolene or farnesene. Okay. So not only that, if you don't want to separate the components, the whole cells can be used. Okay. And this is related to processes such as thermal processes, okay, where you can produce biochar, jet fuel, syngas, and gasoline. Another alternative is to use microbial fuel cells. Okay. And we will look further into that. as we look at the fifth type of conversion, biomass conversion, okay, in the next slide. So just to give you a perspective on microalgae fuel, okay. So traditionally, algae is used to produce biodiesel. Why? Because the cells, okay, depending on the species, so here is one type of algae called Butyrococcus brownie. So actually it secretes oil. If you look under the microscope, okay, this is the cell, all right, and you can see the oil droplets, okay, being secreted from cells. So that makes algae a very interesting choice for biodiesel production. Okay, because in biodiesel production, you actually have to use the oil and you trans-esterify that into the usable diesel. Okay, and that can be a drop-in diesel. So drop-in diesel means that there's no other processes involved. You can just use it directly in the current diesel engine. Okay. So before we go to the electrochemical way of conversion, we just have a brief look at the chemical conversion of biomass. Okay. And like mentioned before, it involves the FT synthesis or Fischer-Tropsch synthesis. Okay. So FT synthesis is actually based on the conversion of a mixture of carbon monoxide and hydrogen into liquid hydrocarbon. Okay. So if you have biomass, so naturally, what is being used currently is natural gas. Okay. Because basically in FT synthesis, you need CO and H2. So what happens if you have biomass is that you need to first gasify that. So it will undergo gasification, okay? And the biomass will be transformed into CO and H2. So once you have that, okay, it will undergo the FT synthesis. Okay? And this is a chemical process. You have a specific catalyst. You have a specific catalyst which will convert the CO and H2 into liquid hydrocarbon. Okay. So depending on the design, depending on the catalyst used, you will be able to tune the fuel that you are going to produce here. Okay. So it's very interesting because not only can this produce fuel, it can also produce the myriad of different chemical products, okay, that naturally comes from fossil fuels that we are using currently. Okay, but this enables us to provide a more sustainable resource for FT synthesis, okay, where we can use biomass. All right. So lastly, we go into the electrochemical, this is number 4, electrochemical conversion of biomass. We still have one more after this, but let's go and look at electrochemical conversion. So basically in electrochemical conversion, it involves fuel cells, okay? And I just want to give, I just want you guys to know about how fuel cell works. So in fuel cells, you will have two compartments. You have your anode and you have your cathode. Okay? And these two compartments will be separated by a membrane. Okay? So you will need hydrogen. Okay, and the hydrogen will go in to the anode part, okay, where the atoms are stripped of their electrons, okay, and the positively charged protons will pass through the membrane. Okay, the positive ones goes there, and the negative is electron, that will flow here. Okay. And as this generates a circuit, okay, it basically generates electricity. Okay. So now the electron is here and the proton is there. It will combine, okay, and produce the fuel cell byproducts, which is water and heat, right? So that is the brief explanation of how fuel cells work. Okay? It's very simplified, okay? And I think it is enough for you guys to, get brief understanding of how it works. So if we're talking specifically about converting biomass to the electrochemical route, it can involve either direct carbon fuel cells or microbial fuel cells. Okay. So in direct carbon fuel cells, you can use solid fuel. Okay. And technically, well, previously people used coal, but in our situation, we can use biomass. Okay. And it requires a very high temperature, and the C will be oxidized in the anode, producing CO2, right? The, the general idea is similar. Okay. The only thing different is that biomass is used instead of hydrogen. Okay. So that is one way to use biomass. Secondly, you can also use microbial fuel cells. Okay. And again, it has two compartments. Okay. And what's interesting is that you can actually use microbes, okay, and wastewater. Okay, so usually people use wastewater to give supply food to the microbes. Okay, and as the microbes grow, right, it will produce hydrogen. Okay, so instead of having an external source of hydrogen, like this case, we have something like this where the microbes will produce its own hydrogen, and that hydrogen, using the same concept as before, okay, will the electron will generate an electricity circuit, and you will be able to get your voltage. You will get your electricity from this system. Okay. So this is very interesting because not only you will be able to generate electricity, you can also treat wastewater. Okay, and that is something that is very, very usable. Okay? It's very applicable in today's world, right? Right. Recapping that, okay, we have the final conversion method, which is the mechanical conversion of biomass. Okay. So if you have wood or agricultural waste materials, okay, something that is in the form of straw, sawdust, slab, sunflower cake, agro waste, okay, you have this fibers basically. Through mechanical processes where you can grind them and then dry it, and then using briquetting methods, you can produce briquettes such as this. Okay? And this can be used for heating and cooking, especially in regions where access to electricity or other fuels are scarce. So remember, if you still remember, I think, was it 2 weeks ago that we looked at the energy consumption. Okay, remember in the African continent, right? The fossil fuel consumption is, there's no data even. Okay, why? Because they weren't able to get access to energy. So there, a lot of people uses whatever they can find. They can use wood, okay, or some wood residues to cook. Okay, so they burn it to cook their food. But in this mechanical conversion, this is very useful for them because they were able, with their agricultural residues, they were able to generate briquettes, which can then be used for cooking. Okay? And if you manage to produce very, very high amounts of briquettes, you can use that for electricity generation. Okay. So it's very interesting. Not only you have to look at the sustainability of a process, we also need to look at the social side of it as well. Okay, we have to make sure that no one is left behind, and we, as a world, okay, as a world citizen, okay, we have an obligation, basically, to ensure that everyone gets access to a good standard of living, right? So not only as world citizen, even in Malaysia, yeah, there are places where constant or continuous access to electricity is still a problem. Okay, so how are we going to help these communities? Okay? This is where you guys come in, guys. You have to, as you go along, okay, not only now, but in the future, okay, when you go through a situation, okay, where you see people less fortunate or people in situations much worse, you have to think about what you can do to help them, right? So I guess that concludes the lecture for today. Okay, so I hope you will get some useful information. Okay, I hope you can understand what are renewable resources, okay, and how we can use technology to produce sustainable energy. Okay, and with that, I thank you. Bye.